Okay, so this is the first video for Unit 1, and from your textbook, it's going to cover sections 2.1, 2.2, and 2.3. So if you want to look through those sections as we're going, they'll help you give more information. Video 2 will cover section 2.4, and then video 3 for this unit is going to cover sections 3.1 to 3.3 on acceleration. So as you're going through this, pause it, take some notes. Also make sure you are answering the questions on the Google form below the video, because that's what we're going to go over in class. Okay, so the main ideas here for section 1 is that we're going to look at these things called motion diagrams and to show how they work. Okay, and you should be able to answer these two main questions after section 2.1. How do motion diagrams represent motion, and how can you use a particle model to represent a moving object? All right, so you notice movement all around you, whether it's watching it with your eyes, whether it's watching on your cell phone, whether it's watching it on TV. You look at movement all around you. Anytime an object changes position, it's movement. Okay, so it can be straight line, it can be curved, it can be a lot of different directions. But this is all about how do we look at and how do we draw and how do we analyze motion. Okay. When an object's in motion, it changes position. Okay, so I have my little cursor here. If I go from here to here, it's in motion. It went from one location to another one. Okay. So for initially here, we're going to look at straight line motion. Okay, and it's going to go between 2 points as it says on the screen. So we need to look at, when we have motion, we need to look at how far it moves and what time interval it takes to travel that. Okay, the first way we're going to do this is we're going to draw what's called a motion diagram. And this is an example of a motion diagram. We have a runner that a bunch of different pictures taken of this runner from a given starting point. Okay, from a given starting point, and every dot represents a time interval. Like let's say, and they're all equal on time intervals. So like this dot is our 0. This could be 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. So every second, a dot would be put down to represent the motion diagram. So it's representing the location of an object in a given amount of time, and if it's moving or not. That's the main thing for motion diagrams here, showing motion and the rate of motion. How far does it travel? Okay, now that's really section 2.1. 2.2 is looking at more of the coordinate systems with graphs. We're going to look at what a coordinate system is and what's the best way to choose a coordinate system to look at where an object is going. Okay, and how are time intervals measured? And we're going to look at a little bit of what's called displacement. Okay. Origin, position, hopefully we're going to learn, and distance and displacement and magnitude. All these terms you're going to need to know by the end of this particular section. Okay. All right. So the coordinate system basically tells you where you're starting. What is the 0 point of your motion? Where are you going? Okay. They're going to have a 0 value. Like on a number line, the 0 would be your origin. Okay, so the origin is where you start and where you start measuring motion from. Okay, so like if we have this video here, or this little piece down here, which could be a motion map, every place here represents so many seconds, and the origin is this 0 meter mark here. Okay, so if you change your location of your origin, you actually change how far this thing actually travels in relation to the origin. So if I place the origin here, he actually starts 5 meters to the left of the origin and ends up only 25 meters to the right of the origin as to where it is right now. So the origin is very subjective. Okay, so this is a straight line motion. Okay, and we can put a measuring tape out from the origin to measure our distance that we traveled. Okay. So every dot represents a certain time interval on like a motion map. Okay. So we would draw an arrow for every 10 seconds or every 30, or excuse me, every 10 seconds or every 30 seconds, however we want to draw this. But you draw an arrow between each dot. Okay. So two arrows locate the runner's position at two different times. So obviously the bottom one is longer because you ran a farther distance. Okay. All right. So length of how far the object is kind of from its origin is its distance. Okay. So like this one is 5 meters to the left. Okay. A position 9 meters to the left of the tree, 5 meters to the left of the origin would be a negative position. So yes, you can have a negative position on this. All right. Now we talk about negatives and positives. Two words you need to know right now are the ideas of vectors and scalars. A vector quantity is something that has a magnitude and a direction. Like 90 miles an hour north is a vector quantity. 8 meters east is a vector quantity. And they're represented by arrows called vectors. Okay. All right. And if they don't have a direction, if they only have a magnitude, it's a scalar. So like temperature, 75 degrees Fahrenheit is a scalar quantity. Okay, so a vector quantity has to have a direction. If it doesn't have a direction, it's a scalar quantity. Because if I tell you to go 8 miles, you have no idea what 8 miles is, and you can end up at a lot of different spots if I just tell you 8 miles. However, if I said 8 miles east, then you know exactly where you're going. Okay. All right. So now we can also look at the time intervals. Okay. We're assuming each of these items here have essentially an equal time interval. Okay. And the common symbol for time interval is this triangle theta. The triangle is delta. Okay, delta in physics is what's called the change in a quantity. So if you see delta something, you're looking at change in. So in this case, we're looking at change in time. So the change in time from this runner from 0 meters to 25 meters is 30 seconds. Okay, well, in this case, it would be 25 seconds. All right. So time interval change is just how long it took you to get there. All right. And then I and F, the TF is your final time minus TI, which is your initial time. So if F is final, I is initial. So like if your final, that a lot of times you would use this if like you weren't starting right away right when you start a stopwatch. Okay, if it was like if you start running when the stopwatch had 5 seconds and you stopped your stopwatch when it said 25 seconds, the time you actually ran was 25 minus 5, which would be 20 seconds. Okay, there's no direction, so it's a scalar quantity. All right, so this little diagram, actually there's multiple things on here. We can look at how far this runner actually moved in relation to a couple different things. Okay, we can look at how far did it run, how far did she run at the tree and the lamppost to get an idea from the origin position. Now the origin is here. If the origin was the tree, that would be a different how far she actually ran in relation to the position, to the origin. So these are vector quantities because they have a magnitude and a direction. Okay. And notice the longer the number, the higher the number, the greater the distance covered, the longer the arrow. That's a big thing too. Okay. So we're looking at change in x. Okay, so xi represents the initial to get to the tree. Total distance is how far it actually ran. Okay, and your difference in those are your delta x, your displacement. Okay, so displacement again is your final position minus your beginning position. So if you think about it this way, if you go around in a circle, you go right back where you started, so your final position will be 0, your initial position will be 0. If you go around in a circle, you don't go, your displacement is 0. Yes, you travel a distance, but you don't travel a displacement. And you can be positive or negative as well. All right, so when you add two vectors together, you get what's called a resultant vector. So if they're going together, if the arrows are going together, your resultant is a larger arrow, a larger resultant vector. If they're going in opposite directions, if one goes east, the other one goes west, your resultant is a smaller vector. Okay. So if they're going in the same direction, you add them together. If they're going opposite directions, you subtract them. Okay. We need to really show that where it's moving, your object's displacement, it needs to be a vector quantity. Okay. And notice that it says here the displacement is not identical to the distance it traveled. Remember, distance is how far you are away from where you started measuring. Your distance is just how far did you go. Okay, the length and direction of the displacement vectors do not, even if you start at one spot and end at the other one, it doesn't matter how you get there. But your displacement from one spot to the next doesn't change, even though you might go all zigzagging all over the place. Okay, the last section for this particular one is putting all this on a graph. So you've done graphing before. Now we're going to spend a lot of time on graphing in this particular course. Okay, so we have this motion map. Every 5 seconds, we have a position. We have a dot. Okay. Okay, but we can graph this rather than leaving it as a motion map like this. We're going to now put it into a graph. And we can very easily figure out using a graph a lot of information. So this is the data table from that motion map. Okay. So at 0 time, it went 0 meters. 1 second, he traveled 5 meters, or they travel 5 meters. This is the data gathered from that motion map. Now what we're going to do is we're going to put this into a graph. And when you do this, the position goes on the y, the time goes on the x. Okay. The time variable for most of the graphs we're going to do in here will always go on the x-axis. Okay, so then each x position, or each dot here, is the position at a given time. And the next video, we're going to look at finding the slopes of these lines. But this graph now shows you where you're at any given point. So you can figure out here at 2.5 seconds, they're about 13 meters out. Okay. So the words, so you have a verbal description, a picture like we showed you with the runner, the motion diagrams with the dots, data tables, and the graphs can all give you the same information. Okay, depending on what you need to find, you'll have to figure out which one is best for you to use. Okay, so now we look at this graph here. Okay, in this graph, when does runner A and B, when does runner A pass runner B? Or B, sorry, when does runner B pass runner A? Well, if you look, B is the lower graph, A is the upper graph. So what time do B and A have the same position? At that point, that's when they cross. And what's the position of runner A and B at this time? So if we look at this, they cross at 45 seconds. Okay, at 45 seconds, they cross. So at 45 seconds, B overtakes A. Now, if we look at this, look at how far they've run. A started at 0 and got up to, that's probably about 180. So runner A traveled about 180 meters. Runner B had to travel 50 meters more than that because they started 50 meters behind runner A. So they traveled like 230 meters in that 45 seconds. Okay. Okay, they're both 190 meters from the origin, but B had to travel that extra 50. Okay. So B passes A about 190 meters beyond the origin, 45 seconds after A passed the origin. Okay, right here. Okay, so you got to figure out what you're looking for and then figure out how to solve it. Now, what you need to do is answer the questions on the Google form below, and you need to score 80% or better on the formatives to be ready for your tests. And when you have questions, please ask in class. We will see you in class.